Have you ever had an idea and wanted to make it real? In this video, I'm taking this rack, break it down, design it part by part, and turn each part into a technical drawing that any mechanical engineer can manufacture. Throughout this video, I will be talking about the reasons behind my choice of feature and choice of technique, why I use a feature the way I do it, why I design a part the way I do it. I want to prepare you to start learning a little bit about DFM, Design for Manufacturing. So it's not gonna be your typical SolidWorks video where I say, go to this menu and click here. And if you wanted to learn SolidWorks, I already have tons of those videos on my channel. So stick around if this is what you wanna learn, and I'm sure you're gonna love it. So let's go. The first part I wanna model is the member. Since this is a very simple tube, it would make sense to go for something off the shelf and not go for something customized. Because if you pay attention to this chart, which compares manufacturing cost and lead time, the top right corner is where it takes the most time and costs the most. And this is not something companies like. You'd want to reduce cost and shorten lead time to stay competitive, because the cheaper your product, the stronger your competitive edge. The way I'm planning to do that is by going after standard components, basically off-the-shelf parts, something I can buy from a website, a production line, or a manufacturer that can already provide it. So instead of extruding a rectangle, I will go here and I would draw a line. Now I would go to members inside the weldment tab, and I would use the 0.63 by 0.38, which gives me the profile I want. That's an off-the-shelf product, and I don't need to make sure if this component exists or look for someone that can manufacture this. So first step, I would need 3 holes on this member. Each of these holes have a function. They act as a hinge once the part is duplicated and connected to each other. I also need to consider their size and location. Obviously, it hinges on both ends and also at the center here. But what's the actual size of the hole? What passes through them? How big should they be? These are the things I'm considering at this point. So next, I'm going to create 3 holes here. I will use Hole Wizard, and these holes should be large enough to accommodate an M4 screw. I will tell you why. Since I'm going to have the M4s move around in it rather easily, I need to activate the custom sizing and change that to 4.1. Now I can save this. Now at this point, several variables are still unknown to us, such as the size of the top rack or the angle of the feet. For example, if I wanted the final rack to stand at this height, the top rack would shrink and the feet angle would be angle X. But if I wanted it shorter or with a larger top area, I'd have to reduce the height, which would also change the cut angle of the feet member. So at this point, I'd prefer to already start my assembly so I can better visualize the issue. Now I need to go and create my mechanism, which is the accordion effect. Now I need 2 of these, so let's duplicate one by holding the control key on the keyboard and dragging one here. If I put this circle on this one and make them coincident, I kind of create that mechanism. But the first component you insert inside the assembly in SolidWorks will be fixed. Now I could right click here and have it float, but then it would be absolutely free with all the degrees of freedom inside this space, which is not what I want. So what I want is for them to be in one place and work symmetric. Therefore, I'm going to use the top plane and have it mated with this surface, so at least I prevent them from going back and forth along the y-axis. If you look at it, I cannot go back and forth, only up and down. But now I'm going to have to kill that too. So let's find the plane, this one, and let's have the axis shown. So this tiny axis here, I'm going to pick it, hold the control key down, and mate it with this one. If I do that, then it would move here, but it would probably only go up and down, which is the last thing I'm gonna have to fix. So I would probably hold this one and this one too and make them coincident, but they are not moving symmetrically. That's not what I want. I want them to move symmetric according to this plane. So I would select that plane, go to mate, go to advanced mate, pick symmetric, and let's pick this and this. Now, I think we're set. This is the accordion effect that we wanted. However, I need another set of these, so I can just duplicate this up. And if I put this one on this one, I have taken care of the first set of my members. That fast and that easy. Done. Now, the next part I want to work on are the shafts that connect these together. So I need another set of members on the other side, but in between, I'm going to have to create shafts. So over here, I have created the holes with a diameter of 4.1 millimeter. Now, the shaft ideally have to go through this. So if the shaft is 4 millimeter, is fine. I could do that, and in fact, I will do that quickly for you just before I change it and tell you why I cannot do that. So first thing first, if I wanted to create a shaft with a diameter of 4 and wall thickness of 1, this is a shaft that we probably can't find in the market. It's standard size, but if I do it like this and say, okay, you two stay here, it would look okay, right? There is a hinge, the shaft goes here, but what would stop this member and this member from moving to the right? There is no shoulder here, there is no stop here, so there is nothing preventing this. Even if we screw something at the end, we would just prevent it from going outside, not inward. So instead of that, I could probably say, hey, yeah, I have an idea. Why don't I create a shoulder here? Yeah, it looks good and it would prevent it from going inward. Sure, but how would you manufacture a shaft that is like this? You're gonna have to go ahead and use a lathe machine to turn such a long shaft, use so much waste, make your component heavier, and customize this. It's not economical. This would push our point on the chart back to the top right corner. Therefore, instead, have this one fixed here, and the diameter should also be bigger. So because the hole is 4.1, I want to look for a shaft which is maybe 5. Why? Because I want it to be larger than the hole that I have. So the shaft is now acting both as a shoulder and the shaft at the same time. But how do I connect this shaft to this side? I just go here and go for the most common standard mechanical component, a bolt. We put a bolt here, which is M4 on default. We just increase its length to 25. So it can go inside the shaft. And we click OK. But if I do this, I would run the risk of tightening this screw too tight, so this member and this member won't be able to move easily anymore. If you assemble this and make it too tight, you lock your mechanism. So how do I prevent that? So I would come here and insert an inner thread inside this shaft, and I will calculate the depth of this inner thread. By the time the screw is inside the shaft all the way, I will leave a 0.2 millimeter gap here, so there is no locking. But how do I do this? First thing first, I would hide one of the members and I would just measure the depth from this surface all the way to the bottom of the screw, which is 5.7. So if I add an inner thread inside my shaft, which is only 5.5 millimeter in depth, then I think I have created that gap that I wanted. But since this is only for the drawing, I would add the cosmetic thread. So we go here and find the M4, not up to next 5.5. So let's go back and show the mates that hold the screw in place. Let's remove that so we can move this out. We said we want this surface to this surface to be at a distance of 5.5 millimeters. And when I do that, I would hope to leave a gap of 0.2 millimeters here, which I am seeing successfully. Where is it? Over here. This is the gap. Let's calculate it one more time. It should be 0.2. It is 0.2. So if I tighten the screw too hard, still I would not lock my mechanism. That's another thing to consider for me. All right, now my screw works also as a hinge, but the other problem is the shaft is extruded blindly. I cannot take advantage of having a mid plane here to mirror these members to the other side. There is no mid plane here. That's why I would go back. I would edit the way I extruded this feature and change it to mid plane. Always do mid plane, guys. If you're starting off with SolidWorks, if you are a fresh engineer, SolidWorks helps you. Go with mid plane. That's my recommendation. Because if I go with mid plane and open my shaft, which is this, I'll see the front plane is here. And I can use this front plane and go ahead and mirror all these components like this to the other side. Done. If I did it the way I did it first time, I could not have done this. Then I had to go and create a custom plane, and you don't want to do that. Instead, what you really want is to let these modeling habits sink into your head until they become second nature. It's not about memorizing tools or tricks. It's about building a way of thinking. So when you're in front of SolidWorks, things just flow. Now, this video isn't the place to go deep on that, but I've already put together a free 30-minute webinar where I walk you through the top 5 modeling habits you should pick up right now. It's on my page. You can find the link on the top right corner or in the description below this video. Now, duplicate these shafts for all of the open holes. So let's do that quickly. Now, since this is a symmetric design, all I have to do is to mirror some of the components, some of the shafts from one side to the other. And by some of, I mean one. This is the top rack, which we have to introduce here. On one side, it has to go inside these 2 holes and act as a hinge. On the other side, it has to be folded and also be sitting on top of here and gets locked. So how do I do this? First, let's measure the rough distance between this hole and this one in this stage. This is about 339. So let's go for 350, okay? But since we need a set of components assembled together to work as a group inside the main assembly, we first need to create a sub-assembly for the top rack parts. That way, we can bring everything pre-assembled into the main assembly. The first component is drawn, then extruded. Then the circles are added. Now the question is, do we want each hole large enough to fully accommodate the shafts, or do we want the holes smaller like the members, so the shafts rest on the inner surface? To answer this, we look at the rack assembly from the top. If this sub-assembly sits between the inner members, then this distance equals the shaft length. But if it sits between the outer members, that would be a different length. We choose the inner one. That means our side components must sit on the inside, so the shafts must fit inside these components. Therefore, the diameters need to be slightly larger than 5 millimeters, say 5.1, to accommodate the shafts. So now, let's design this side component. At this point, I'm going to create a sub-assembly. So starting with the first side component, I draw a center slot. This center slot will accommodate, let's say, 3 to 4 shafts. So I have the length and I draw a circle to accommodate the shaft on one end. Since the shaft is 5 millimeter in diameter and we want to fit it inside this, 5.1, and let's use linear pattern to create 4 of them, dragging the last circle on the last point to make it fully defined. Now I can just go ahead and extrude this, let's say for 10, mid plane is fine. I now create the first assembly, a new one, because I'm going to use this assembly as a sub-assembly in the main one. So I just bring the shaft and fix it inside here. Done. Now I need 4 more. I can use linear pattern in the assembly mode, picking the shaft along this X for divided by 3 gives me the right value. Yep. I would need 3 because the last one is an exception. I will tell you why in a second. So let's just go ahead, open the shaft, use the front plane and mirror this side component. But at this point, we face a new challenge. The rack has an inner member on one side and an outer member on the other side. The distance on the side of the sub-assembly is designed for the inner member. So on this side, we would need a longer shaft to extend down and lock into both members. But that would create another challenge of its own. For now, we start by creating a new configuration for an extended shaft. Therefore, bring the main shaft here. Now, the extended shaft is here. Width is the type of mate I need. So these two ends are on the red components. Now I pick the ends on the extended shaft. This end and this end. That looks good. And I can save this sub-assembly in order to bring it into the main assembly. Now, in order to make sure the side components don't move right or left, basically to ensure everything you see right now is fixed together, we need a mechanism to hold the shafts and the side components tight. I'm thinking of adding 4 holes on each side component and using M3 countersunk screws. That way, the screws sit flush and connect the shafts to the side components. Using only 8 screws, we could achieve this. Placing the screws is easy. If I change the view to wireframe, I can see the holes and place my real holes directly in the center. This could also be done by measuring and adding dimensions. Then I'd use the library tools to bring the screws. Choose countersunk M3, adjust their length, and add 8 of them into the sub-assembly before bringing it into the final assembly. But this is a design intent question. You have to assume that once the rack is empty, it's one situation, but once you put wet cloth on it, applying weight, you're pushing it down. Now, if I lock the upper top rack from the top while pushing it down, it actually becomes self-locking. The more weight applied, the more secure it gets. That's because the force presses it tighter into place. But if I lock it from the bottom, then nothing prevents it from shifting left or right, and then the entire structure could collapse under load on the other side. That's not what we want. So a good design should lock from the top. If I go from the top, I need to consider the next steps carefully. Or if I go from the bottom, I risk instability. Therefore, in order to open some entrance for this shaft on this member, I need to first consider one thing. If I change this member here, I'll be changing all the other members. And since I don't want it, I'm going to have to go to my member and create a new configuration for it. That would allow me to create an exception for this member. So if I go to the configuration manager, right click and add a configuration and add locking mechanism. Then I get to go back here and apply whatever I want to do to this design tree, and it would just change one of the configurations. So how do I do this? First, do I open a gap here, here, here? How do I do this? I know it's hinging around this axis. So in order to do that, I'm gonna first go here in the assembly mode, click on the member I want to change, click here and go edit part. Now I want to edit this part, right? And I know for a fact I want to draw on this surface. Okay, what do I want to draw? I want to draw a circle that starts from this opposing axis here. It's concentric to that. And it goes all the way to the center of the other one circle. So this line is the path where this longer shaft on the top rack part moves along. So if I want to create an opening, I need to just open it from here to here. So let's just go to offset. The shaft is 5. So if I offset this line for 3, just to give it some space, because offsetting it in 2 directions. I'm offsetting it by directional and changing this line to base geometry. That's what I mean. Very well. Okay, theoretically, it looks good. Theoretically. I still have to deal with a lot of issues with the mate. Probably the last concentric is the issue. I'm gonna delete it, it's fine. At the very least, when I put some weight on the top rack, it's not gonna fall down. But cutting a component like this with having such a narrow component there, it's not reasonable nor it's wise. So we're gonna have to change our cut a little bit. I can just add some new feature to it for the ease of use. For example, I can just get rid of this top half. It works, but having sharp edges like this for a end customer product is not something I would recommend. What do? I recommend rounding this. I could just round this. This is too big. Maybe with one. Okay, looks a lot nicer. However, this thing is not in the right place. So let's have this one tangential to here for the locking mechanism. And boom, something like that. All right, next, I need to answer a few questions myself. Is it ready? No, I don't think so. Why? All these ends are open, so we need to close them with caps. It just have to be a small, simple, normal cap. Nothing too fancy, so let's see what we find out. Like this. Now the cap is added. Let's change the transparency. Is this cap interfering with this bolt? No, it's not. So we can leave it at that. And let's add all the caps. Oh, this one needs a special cap. So let's remove this one. And that one needs a special cap too. I will tell you why in a second. So let's just add all the caps. Okay, so to this point, everything is fine. It would hinge here and it would make sense. It would come down here. And the more we put pressure on it, this wall on the back here would prevent this from collapsing. So this one. Now, I need to take something else into account. When this is closed like that, so when we put too much weight, it tries to collapse and it would stop here. Right? And at this point, I need to ask myself, do I want my rack to be sitting on this 4 small lines, or do I want a flat surface? For stability, I would prefer a flat surface. But like the top member here, which was an exception, if I change the bottom one, I'll be needing to create a new configuration once more. So let's do that. Let's go to this member and create a new configuration. And let's call it the foot. Now we are on the foot configuration and I need to know which side to cut. And since I don't know if I make any changes, it would apply to this end or to this end, I have already changed the color of one side here. So I know I need to be changing the side that is green. So not this end, but this end where we have the green. But if I create a new drawing, I don't know, do I cut it at this angle, this angle, this angle? I don't know anything. What do I do to find it? I use the assembly to find this information. I edit this part, edit the part. Now, new drawing. I know for a fact this would sit here. Like if this was our ground, this is the angle I cut. But then we have a hole here, which is ugly. Do I want to cut a little bit above it, making everything shorter? Sure, why not? Let's do that. Get rid of this and have this one tangential to the circle. And we want to have the ground. And since I don't have any reference for it except the front plane, let's have these two parallel with each other. Now, all I have to do is to close this sketch and cut through it. But look what happened on the other side. Doesn't matter. We dealt with this before. I think we got it. All I have to do is to go to shaft, mirror these two and see if I see any errors. No errors. That's good. Now let's add that weird cap inside the way I do it. Okay, I would do it like this, but if I go back, we have some issues because now they are one single component. what I would like to do is to get rid of this first, save it, and then try to open this component, which is the member. Let's duplicate it here and call it cap 3, and then open cap 3, then reverse the delete component, and then click OK. So now, or change the color. Now here I can just bring cap 3, and I know for a fact that it fits. If I go like that, it would definitely fit. Like that. And then we have to take care of how we're gonna connect these two together and what this component is actually made of. Is it 3D printed? Is it injection molded? What is it? Probably best would be to maybe even have it hollowed. However, since I don't know any of this right now, I don't know what to do, and I'm gonna leave it at that. And then we can glue it there. Now we can use the front plane on the shaft. Look how beneficial it is, how many times I have benefited from this throughout this project. Boom. The last thing we want to do is to add another cap on the bottom if we want to make sure it is sitting perfectly on the floor, and move on to the drawing. So let's do that quickly. Now we can bring the cap foot too, and we know for a fact they would fit perfectly like this. Again, mirror. Look how beneficial it is to extrude things mid-plane. Okay, I think it's done. And we need to also take into account how to connect these caps, this and this particularly, to the members. Is it glue? Is it welded? Is it screwed? We need to do that. Now, let's move on to making the drawing for it. The sheet format is not scaled correctly, so let's go 1 to 5. I think it's good. Now, at least we can see the final dimensions on the fully assembled rack. I don't like, oh, 666. What are the odds? Good. The height is almost good, like a cabinet, including the bolts. We have bolt to bolt, 1 meter. It's 66 centimeters tall, 37 wide, and about 1 meter long. Now we want to create the bill of materials as well as the individual drawing of each component. We could add a new sheet here, go here and bring the current view like that, and create a bill of materials. So insert, tables, and bill of materials. A top level only or parts only. Let's go with parts only, because if I go top level, this whole sub assembly we have created will be counted as one component. So instead I want to go with parts only, and I get 8 different components. Now, I don't know what's what, so we can go to annotations, use auto balloon to assign numbers to this drawing, so we know what's what. Do we have 1 through 8? 1, 2, 3, 4 is missing. What is 4? That the view is not helping us to see 4. 5, 6, 7 is missing too. What is 7? Cap 3, which is there, right? So what I do is I would add another view up here. Since now the scale is too much, I'm gonna have to change the scale on the sheet number 2, change it to 1 to 10, so we have more space to work. These are on magnetic lines, so I can just move the magnetic line. They follow order. Good. And now I'm gonna bring this, and we said number 4, which is the pin. So let's create a detailed view from this side that covers both number 4 and number. Now I can bring detail 1 closer, bring it down here, select detail A, Then auto balloon. So we get number 4 and number 7 on the detail view, a lot cleaner, and we know what's what. And since it's not clear, I might be considering to change that into a color view, so whoever is viewing this knows what's what. At this point, we can go ahead and create individual drawings for each of these components. Okay, so let's start by creating the drawing for the top rack sub-assembly. I would like to increase the scale because these components are small, but if I do that, the whole component would not fit into the sheet. So I would use the break view to make it smaller. This way, everything fits onto the sheet and I get to see all those small features clearly. Because if I reduce the scale until it fits, I could not see the components in the bill of materials. Speaking of which, let's add that over here. Now we need to add some numbered balloons to each component so we can associate those components with the bill of materials. This way we can distinguish them clearly in the bill of material like this. Now let's add some dimensions. And this is done. Next, I would like to create a drawing for my members. Since I have 3 different versions and they are almost similar, I would like to include all 3 in one drawing. You could have them individually, but in this case, since it's not for batch production and more of a one-off project, I will include all 3 similar components in one drawing. Adding the dimensions is also easy. But every time I see a dimension that has decimals, like tenth or hundredth of a millimeter, I should ask myself, does a rack needs to be so accurate down to 10 microns or even 100 microns? No, it doesn't. So I will just reduce the decimals to 0 to stay clear of that and reduce manufacturing costs. Because if you want to manufacture it down to the second decimal, it would increase the cost significantly. Also, here on this opening, this was made by a circle, so it has a radius, but it doesn't need to be that way. If it's a short straight line, it still works. So I would use a center line to be able to use an angle instead. And just like the dimensions, the angles don't need decimals. 42.4 degrees is an overkill. It would increase the cost, if not make it impossible. I could reduce all of that and make sure there are no decimals here. But for a drawing like this, since I didn't draw it in the beginning this way, I would like to run a test. I usually take the dimensions I have, a screenshot the drawing, and try to recreate it based on the way I dimensioned it. This way I can check that it's not overdefined or impossible to manufacture. That's what I would do here. And it seems to me that it's working. So it's acceptable. We save it and move on. Next, I would like to start with the side component. Let's bring it here, fix the scale, and create a cross-section view. As I was adding the dimensions, I realized this is a very solid and thick material. It's not necessary. Why waste so much raw material when we could remove some to make it lighter and cheaper? But for now, I'll just add the essential dimensions before making any changes. This is a whole call out. This is the thickness. We need to add tolerances to make sure the shaft will fit here. Usually in assemblies, I cross-check every component against the counterpart later and after I'm done with the drawing. This is just preliminary, but you need to do that too, because shafts are going to go inside these openings. I would save this, but at this point I like to create some cavities. Since this is a solid material and changing one side would potentially change the wrong side in the assembly, I'll change the color of the outer side so I know what's inside versus outside. That way when I edit, I work on the interior and not the exterior. Now, shelling would not be practical here because of the M3 countersunk holes that would make manufacturing this component impossible. At this point, I would use a SolidWorks Course Pro GPT in ChatGPT. It's free to use and I've spent days to make it. It works perfectly. You can search for SolidWorks Course Pro in GPTs, upload your screenshot and ask your questions. I'm going to put the link to that GPT on the top right corner of the screen here. I did the same thing, asked if it was possible for an injection molding. I didn't like the answer, so I'm changing the approach and making it simpler. Instead of using shell, I'm using a boundary down with an offset from all edges, then extrude cut straight down. This way, the tunnels connecting the M3 countersunk holes won't be an issue. The draft analysis looks okay. Again, I gave it to the same GPT from SolidWorks Course Pro. Take pictures, upload, ask your questions. I'll put the link in the top right corner. If you click here, you get to use it. It will help you a lot. Looks good. Back to drawing. We need to update the height or the depth of this cut and add a couple of radiuses. This radius and this one, plus the wall thickness. 145 should be fine. Not too thin. We could make it thicker after talking to the manufacturer later, but for now I'll roll with that. I'll define the depth of the cut through another cross-sectional view. Section BB from here to here is 7. Right now, this drawing looks much better. Just like before, we don't need decimals. I'll remove them, keeping only 1 decimal where necessary, or none at all. 2 decimals is too much and makes the part unnecessarily expensive. The draft angle analysis looks okay. Even in the assembly, it looks perfect. At least we've removed 40 to 50% of the mass. Next, we have the shaft drawing. There are 2 configurations, normal size and extended size. Let's fix the scale of the sheet. Again, I'll go larger so I can see the diameter sideways, then larger again, and break the view so the whole component fits. If you feel like it's too short, you can drag the break line to make it longer, but I think it's okay. I activate the hidden lines. The depth was 5.5 if you recall, so this is the total length with the tolerances for the outer diameter, so the manufacturer knows what's acceptable. I define the tolerances for the length, let's say ±1. We're flexible enough, we could even go to 2, and I don't think that would cause any problems. Now I'll bring another shaft at the same angle, just changing its configuration to address the extended version, just like the members where we did 3 of them in one drawing. Here we'll do 2 in one. Purposefully, I'll leave this a little longer so with the naked eye you can see the difference between the 2. I'll copy the tolerance format onto this dimension so I don't assign it twice. And if you recall, the extended version doesn't have any inner threads like the normal version. I'll write its name directly on the drawing so the difference is clear. Now, since this will fit inside the side component of the top rack sub-assembly, I'll open them side by side and check that the tolerance work in our favor. This is the shaft and this is the hole in the side component. The hole is 5.1 and can go up to 5.15. The shaft tolerances are between 5 and 5.10. So worst case, if the hole is 5.15 and the shaft is 5, the gap is too big. If both are 5.10, then it's tight. But since the side component is plastic, even 5.10 and 5.10 will work with a little pressure, and a tighter fit is actually better. If both were metal, that would be risky and unwise. But since the shaft is metal and the side is plastic, this works fine. Next, we have the cap 3. Assigning the dimensions again. Double check tolerances against the interior of the member. Open both drawings side by side, 12.75 against 6.4. I noticed I gave the tolerance to the wrong side. That was the length and it does not need tolerance. That was a mistake, so I'll remove it. Instead, this one needs the tolerance. It can be slightly smaller, but not larger. Same for this 6.40. Let's adjust the tolerance to 50 microns. Next, we have end cap number 1. Let's create a drawing for it. Again, we run this against the inner sides of the member, making sure tolerances are in our favor. Since it has to fit into a standard off-the-shelf component, the members, I won't remove decimals here. These are exceptions. We need them because we saved already on the members, and these components have to follow order. And lastly, we have the last end cap that goes on the foot. Set the scale right, same concept, check against the inner size of the members, and assign tolerances properly. Again, decimals don't need to be so accurate. Now we add the top view and its dimensions. 6.40 is one of the dimensions that needs tolerancing. Again, check against the member to ensure the tolerance is on the correct dimension. I noticed we don't have 1275 here. This came up during cross-checking, so I'll add it. It would be from here to here. Now we can assign the last tolerance, and this drawing is ready for our colleagues to review. So now we've got a full rack, parts designed, assembled, and even drawings made. You've seen how little details like a shaft fits or how deep a thread goes changes how realistic your design is. But this rack isn't ready for manufacturing yet. If we were to build it for real, we'd still add some things like washers at the end of the shafts. Maybe a better locking mechanism. That's just how engineering goes. Every time you peel one layer back, there is another one waiting. It's the same with SolidWorks. You might think you've got it until one small habit or shortcut destroys your model. That's why I made a free webinar where I break down the most common mistakes beginners make and how to avoid them. You'll find the link right below this video. And lastly, if you enjoyed this video and want to watch another like it, please hit the subscribe button and like the video. That's the only way you can support my channel to make more videos like this for you. Thank you very much for watching. Hope to see you soon. If you like this video, you're gonna love the video on the right, and YouTube also thinks you're gonna love the video on the left, so make sure to check them out.